Good morning, everyone. I hope you're all doing well. Welcome to Monday morning in the Henderson household. So, let's take a quick peek at the syllabus before we move on. Oh, let me share my screen with you. That would help, wouldn't it? Okay, so you do have a test that's currently open. You want to be taking it. If you haven't already taken it, you want to take it by midnight. It is chapter 6, 7, and 8. It is really math-based, so just be prepared to, maybe have a piece of scratch paper, a good calculator, and some of your notes, because you're going to be doing a lot of mathing. Yeah, so get that done by tonight at midnight. We also, we're moving into the last section. So gas laws, solutions, and acids and bases. We literally have 3 chapters, and then the 4th test and a final. So it's going to move really, really quickly. Not this week, but next week is Thanksgiving. So it will not be, well, I don't know if it'll interfere with us. I'm going to see how I feel. We will definitely meet on Monday of Thanksgiving week. I don't know if we'll meet on Wednesday. Maybe we'll blow that off, as long as we're in a good position with lecture. I'll let y'all know though. So I think that the class will actually start to feel a little bit easier in this last section. Gases, solutions, and acids and bases at this level in chemistry is, I think, easier than chapter 6, 7, and 8. So hopefully this will be a breath of fresh air. There's still math. Math is definitely happening, but we're not going to have as much critical thinking in at least this next chapter for gas laws. It's going to be a lot of plug and chug. So let's get into it. Okay, so chapter 11 is going to be all about gases. Now, we can't apply any of these things to liquids. We can't apply them to solids, and we can't apply them to aqueous materials. Gases, because of their unique properties, specifically of having such a low density and being really far away, they behave in a very consistent way. So these slides talk about straws in the very, very beginning. It always sort of seems random, but we've got this kid with this straw, and I don't know if anyone ever did that when you were a kid, but you stuck a bunch of straws together and saw how long your straw could be. Well, there is actually a specific length that this straw could be before. It doesn't matter if you were the best soda drinker in the world with a perfect vacuum. You wouldn't be able to suck the liquid to the height of your mouth. How long is that? It's still pretty long, but it would be 10.3 meters or 34 feet. Anything longer than that, even if it was a perfect seal, perfect rigid walls, a perfect vacuum, it wouldn't work. And why is that the case? Well, because of the mechanism that allows a straw to work. So first we need to talk about pressure. So gases exert pressure on a surface. If we have let's say your morning coffee right here, and we've got your morning coffee right here, and this is the surface of the coffee. Well, the atmosphere or the air that's sitting above your coffee is exerting a certain amount of pressure. So the gas molecules are bumping into the surface. Now that pressure is dependent on how much gas is sitting above the surface of your material. So if we're at sea level, it would be 1 atm. We're a little bit higher up from sea level, so we're just slightly less than 1 atm. So when looking at what's happening in a straw, if the straw is open-ended, nobody's sucking on the straw, Well, you have a pressure that's being exerted on the outside of the liquid, and it's equal to the pressure that's being exerted on the inside of the straw, because the straw is also open to the atmosphere. So the gas has filled this straw and they're exerting equal pressure. So what happens is the liquid height stays even inside and inside the straw and outside the straw. Now, when somebody comes along and sucks a straw, what happens is you are removing air from the straw. All right, so these air particles that are hitting the surface, you're taking some of those out or creating a vacuum. When you do that, the pressure inside the straw is going to be lower than the pressure outside the straw. The pressure outside the straw is still at your, let's say we're at 1 ATM, we're at sea level. The pressure inside is being lowered. So what will happen is this will push down on the liquid and it will force the liquid up the straw. So this liquid will then, at some point, you've created so little gas that the liquid will then meet your mouth. Now, if we had a liquid and they were exerting, 1 ATM of pressure, and we have this long straw or a vacuum, it's not even a straw, it's like a perfect vacuum, and there's a pump at the end and it's a glass tube, the amount of pressure outside is still going to stay 1 ATM. So even if we create a perfect vacuum here, this thing can only get to the height of 10.3 meters. So if anybody, if anyone wants a hint of extra credit, you could string a bunch of straws together and see how far you can get the liquid. I'm guessing you probably wouldn't be able to get it to 10.3 meters. So how does this relate? Well, straws work because sucking creates a pressure difference, right? So we lower the pressure inside the straw, the outside of the straw's pressure stays consistent. That's how we're able to drink. This idea of pressure differentials is super, super important. This is why we have weather systems. This is why you can blow up tires and balloons. This is why your lungs can inflate and deflate with an inhale and an exhale. So getting back to what makes gases so unique, we have this theory here called the kinetic molecular theory. And this theory is for ideal gases. And it works pretty well most of the time. There are situations where gases aren't ideal, and we'll talk a little bit about that later. But for the most part, we can follow these. So let's see what some of the rules are. They're not rules, but the theories are. One, so if we have a bunch of gas, if it is in fact a gas, we can assume that these particles are in constant motion. Okay, so they're constantly moving. Because there is such a low density, or there is a lot of volume between these things, and because they're moving so fast, because they're a gas, so they have a lot of kinetic energy, so these things are zipping by each other, there isn't going to be any sort of attractive or repulsive quality between adjacent particles. So they're not going to interact with each other. We can kind of think of them all as just individual particles. They're like solo. They're doing their own thing. They just happen to be in a container with others. We can assume that there's a lot of space between particles compared to the size of the particles themselves. And then the speed of the particles will increase as we increase the temperature, which is sort of a no-brainer. So if I put a flame underneath this gas and I start to heat this gas up even hotter than what it already is, I'm going to expect those particles to move faster. Here's same thing. One thing that they add here is it's a collection of particles in constant, and then they say straight line motion. Okay. The gas particles will not attract or repel each other. They don't interact. They're sort of independent of each other. There's a lot of space between the gas particles compared to the size. And then they are going to increase kinetic energy as you increase the temperature. As the temperature goes up, and we use this in kelvins, it's proportional to the energy that the gas has. So because of these properties, the kinetic molecular theory is actually consistent with some of the properties that we have of gases. One of those things is that gases are compressible. So remember, of the 3 states of matter, gases were the only ones that would expand and contract in volume, which makes sense. If we don't have very much volume to the actual gas, it's mostly empty space, there's a lot of room to smush those gas particles closer together. In addition, if they're not interacting with each other, they're not going to clump together, then if we release that gas into a larger space, it has the ability to spread out or to fill its entire container. So a little container like a mason jar size of gas, of compressed gas, we open that up into an auditorium and that gas will spread out in all directions until it's evenly dispersed. That goes along with gases assume the shape and volume of their container. And then gases have low densities in comparison with liquids and solids. These things are all consistent with our idea of the kinetic molecular theory. So here is some gas in a piston, and we can in fact compress this. We're not going to be able to compress a liquid because they're just too packed together. Gases assume the shape of their container. So we've got all these gases and they're going to spread out. These gas particles are going to spread out in the entire container. And because the gas molecules there's so few of them, we can almost say that they're negligible to the volume of the container. Now, again, that's for ideal gases. It's not always true, but we'd say, you know, that these gases are taking up the volume of the mason jar. And then also that gases are a very, very low density. So one way to think about it is if I had a can of pop and I heated it up and converted it into pure gas, so gaseous pop, one can would take up 1,700 cans of gaseous version. This is at 100 degrees Celsius. So that is quite a big difference in volume. So back to this idea of pressure. Pressure is the result of constant collisions between atoms or molecules in a gas and the surface around them. So your body right now is experiencing a certain amount of pressure. You can't really feel it. Our body is so accustomed to it, but there are little collisions hitting your face, your arms, all over your body that is creating a pressure, which again, here we're probably 0.95 ATMs. Pressure is super important. It allows us to do all these things. Drink out of straws, inflate basketballs, super fun stuff, but probably more important, being able to move air in and out of our lungs. Also gives us weather systems. And pressure does a bunch of other things. So one way your body can sort of register or feel changes in pressure are if you are, I wouldn't say climbing a mountain. Unless you're like running up that mountain as fast as you possibly can, maybe you could, but more so being in an airplane. So our eardrum has this very thin sort of membrane that separates the inside and the outside of our body, and it creates a sort of a seal. Okay? When we are in equilibrium with the atmosphere around us, we don't notice any sort of sensation in our ear, right? Unless you happen to be sick or something. But what happens is when we go up in an airplane, the amount of gas outside of our ear, so on this side, lowers. The pressure inside our body is still relatively high, right? So what ends up happening is that this membrane in our eardrum will actually curve out and you'll feel it. Your ear kind of feels icky, right? Like, ugh. And so what do you do when you're on an airplane? You chew gum, you try and pop your ears, you open and close your jaw. You're trying to do something to equalize the pressure inside your body with that new pressure outside. And then the same thing is true when you're going down in your airplane. Your inner body has now had equalized with the lower pressure of the airplane. When the airplane goes down, the pressure outside increases, the internal pressure is still low. So this will actually start to bow in the other direction. And what do? Again, you chew gum, you try and pop your ears so that you can have that balance because it doesn't feel good. So this pressure has an actual formula for it, and it's force over area. And so if your force is large and your area is small, you have a large pressure. If your force is really weak and your area is very big, your pressure will be much lower. So here's a lower pressure situation, and then the mason jar on the bottom is a higher pressure situation. Here we can see less gas over the same surface, right? So less collisions. Down here, it's the same surface area, so it's the same container, but there's more gas packed into it. We would expect this to be a higher pressure situation. So the fewer the gas particles, the lower the pressure. Here are some of the units for pressure. The one that we use most readily in chemistry is the atmosphere, or the ATM. The standard unit, or the SI unit, is the Pascal. You may see Pascal also written as kilopascal. Don't be freaked out by kilopascal. Kilopascal is just 1,000 pascals. What is a Pascal? Well, a Pascal is defined as, if anyone's ever taken physics, it's 1 Newton per square meter, okay? And remember, pressure is a force, and Newton is a unit of force, per area, meter squared. In general, the Pascal is much smaller than the ATM, all right? So this is a teeny tiny value compared to ATM, and here are the actual relationships between those two. Another common unit of pressure is millimeters of mercury, mmHgs. You may see this a lot if you're into looking at weather systems, which I kind of am. I've always been sort of a weather nerd. And you'll see, you know, oh, it's 700 and there's a low pressure, 720 mm's coming through, right? They're talking about differences of pressure using this. So what is a millimeter of mercury? Well, at 1 ATM, so at 1 atmosphere, sea level, if we had a perfect vacuum, the pressure exerted from 1 ATM would force mercury, specifically mercury. Oh, no worries, Harley. Up to a height of 760 millimeters. 760 millimeters would be 76 centimeters, okay? Or 0.76 meters, so it's not even a full meter. But this is a consistent thing. So 1 ATM is going to equal 760 millimeters of mercury. Again, at 1 ATM, this is the height that we would get. There's another unit called a torr. And a millimeter of mercury and a torr are directly equivalent to each other. So if I say, hey, I have 740 torr, it's the same thing as saying I have 740 mmHgs. Less useful, or not useful, but less common in science, maybe more common for you, are PSI, or pounds per square inch, right? So 1 ATM is equivalent to about 14.7 PSI. You may be more comfortable with this if you're used to filling up bike tires and car tires and things like that. So we've got all the units here. So, you know, you will have to be able to convert between these. Nothing more challenging than what your normal conversions are. It's just new conversion factors. So here they go through, hey, convert 0.311 ATMs into millimeters of mercury. Well, we can see that we'll use this relationship between ATMs, atmospheres, and millimeters of mercury. One of those is 760 millimeters of mercury. Put the 1 ATM on the bottom so they cancel, put the millimeters of mercury on the top, and we find that 0.311 ATMs is equivalent to 236 mmHgs. So why airplane cabins are pressurized? So they do pressurize the cabins. They aren't, airplane cabins won't be as pressurized as what's happening at the surface of the earth. That's why your ears, pop. But they do have to pressurize them to some extent because you're flying so high in the air. When you're at, 40,000 feet, you're dealing with a pressure that's a half ATM. That means that your body will receive half of the air that it normally receives very, very quickly, right? You've had no time to adjust or become accustomed to this. So you could experience lower levels of oxygen, which would make you dizzy and give you a headache, and you might be unconscious. So that's why they have those freaky masks that pop down in your airplane in case the cabin depressurizes. It gives you a steady stream of oxygen. So because all of these gases follow the kinetic molecular theory, ideally, we have all these relationships between a couple different properties. So all the things we're going to be looking at with the next set of laws, pressure, volume, temperature, amount. Okay, pressure is going to be in ATMs for the most part. Volume is going to be in liters for the most part. Temperature, we like to see that in Kelvin. An amount of gas is going to be in moles. Okay, so all these next couple equations are going to relate all these things together. This first law is called Boyle's law, and it relates pressure and volume. So with this law, we're assuming, so looking at this, we're assuming that temperature and the amount of gas stay constant. We're only going to check out how pressure and volume relate to each other. And these two things, pressure and volume, are inversely related. So when I say they're inversely related, I could say pressure is inversely related to volume. As one goes up, the other goes down, right? Or as one goes down, the other one will go up. So an example of this in real life is a bike pump. So when you have a bike pump and you have the plunger all the way at the top, okay, and you start to push down. In this instance, you have a really big volume and it's a relatively low pressure, right? It's easy to push the plunger down. Now, when you get towards the bottom of that downstroke, what has happened to the volume? The volume is much smaller. The pressure is a lot greater. It's much harder to push on this plunger towards the bottom of the bike pump than up towards the top. So Boyle's law was discovered by a guy named Boyle. We've got this inverse proportionality, and I don't even think it gives us the equation. It talks about a bunch of different things, and it doesn't even give us the equation. So the equation for this is, what's up here? Crap. We'll just go over here. All right, so Boyle's law. You can give yourself a note that says constant T and N, constant temperature and amount. Volume is inversely related to pressure. One goes up, the other goes down. And the equation is V1, scratch that, V1 P1 equals V2 P2. Or the initial volume times the initial pressure is equal to the final volume times the final pressure. So in all these first like 3 or so equations that we look at, there is some sort of change in the conditions. So the volume will change or the pressure will change. In this equation, we have 4 variables. So you would be given 3 of the 4 variables and solve for the 4th. Make sure that you're, for your ones, you're putting your initial stuff there. Make sure for your 2s, you're putting your final. You don't want to put like the initial pressure with the final volume and the final pressure with the initial volume. So let's try an example of this. Straws, straws, straws. All right, so we've got this guy here. So it says a cylinder equipped with a movable piston has an applied pressure of 1 atm and a volume of 6 liters. What is the volume of the cylinder if the applied pressure is decreased to 1 atm? So how would I know that this needs to be Boyle's law or use Boyle's law outside of the fact that it's written right here? Well, it doesn't say anything about temperature. So we're not dealing, so no temp and also no change in amount. So change in N being moles. But there is a change in value, right? I have initial parameters and then I have a final parameter. So this is all leading me in the direction of, okay, I'm gonna need to use P1 V1 equals P2 V2 or V1 P1, doesn't matter which one you put those in. So I need to organize the information from the word problem into the correct variables. So let's see. It has an applied pressure of 4 atm. So this here and this here are my initial set of parameters. I have a pressure of 4 atms, 4.0 atms. I have an initial volume of 6.0 liters. What is the volume of the cylinder if the applied pressure is decreased to 1 atm? So I know what the final pressure is. It's dropped to 1.0 atm. I want to figure out the final volume. Now, I know what is happening here is an indirect or inverse relationship. So my pressure has decreased by a factor of 4. So this should increase by a factor of 4. But we're going to plug it into our equation. Some people like to plug it into the equation and then isolate for the variables. I tend to like to isolate for the variable and then plug in. So I've got V2 here. I want that by itself. So what do I have to do to P2? I got to get rid of P2. So I'm going to divide P2 and P2. So my new equation is V2 is equal to P1 V1 all over P2. This is just variable isolation, which I know can give people a tough time. So you may want to practice those outside of this. Make sure you're keeping the 1s and the 2s with the right thing. Don't all of a sudden flip this to a 2 and this to a 1, because that will change your answer. So V2 should equal my initial pressure, which we said was 4.0 atm, times my initial volume, which is 6.0 liters, divided by my second pressure, 1 atm, 1.0 atm. All right, atms will cancel and we'll be left with units of liters. V2 is equal to, well, 4 divided by, or 4 times 6 is 24 divided by 1 is 24. So we get 24 liters. Now, with Boyle's law, it's okay if this was in mmHgs and this was in milliliters. That's not a problem when we're dealing with this equation. When we get into the ideal gas law, which is a little bit later, we need to have specific units. But for this, they can be whatever. They just have to be in the same unit. So if this is in ATMs, this needs to be in ATMs. You can't have 2 different units to use the equation. So I'm going to give you another problem working with Boyle's law. Okay. make that 3.0 so that we're not out of sig figs. All right, so what is the final pressure of a gas at 730 mmHgs that decreases from a volume of 28 milliliters to 3 milliliters? I'll give you all 3 minutes to do that one. All right, so when looking at this problem, it's not saying anything about temperature. It's not saying anything about amount of gas. It's talking about a change in pressure and a change in volume. So I know I need to use P1 V1 equals P2. Whoa, hello, P2, V2. I don't care if you know that this is Boyle's law, just be comfortable with the relationship. So this is in millimeters of mercury. This is in milliliters and milliliters. That's fine. They're in the same units. P1, V1, P2, V2. Just know that the equation will end up popping out your final pressure in the millimeters of mercury. So we set our initial pressure here. In this case is 730 mmHg. And the gas originally took up 28 milliliters. So this is a really tiny amount. We want to figure out what is the final pressure if I'm going to decrease this to 3.0 milliliters. Okay, well, think about what's happening here. We've got a pressure of 730 mmHgs, and it's taking up a space of 28 milliliters. I'm going to take that gas and I'm going to smush it into 3 milliliters, much smaller space. So I would expect that the pressure is going to skyrocket here. Let's see what happens. So we want to go for P2. I'll solve it by plugging it in without isolating. So P1 is 730 mmHg times V1, which is 28 milliliters, equals P2, which is what we're trying to find, times the 3.0 milliliters. All right, if you like to do it like this and then divide it out, no problem. All right, so we're going to divide the 3.0 milliliters over here. Let's see, we've got our 730 times 28 divided by 3. Oh yeah, we got a big pressure here. We've got 6813 mmHgs, and really, you know, we've only got 2 sig figs, so it's probably better to put this as 68 0, 0. While we're at it, let's say that in the problem, what is the final pressure in ATM? So I'm changing it a little bit. I want you to tell me what the pressure is in ATM. So what is it? Converting it. I'm going to give you just a minute to do that. 2 minutes. Okay, so for this one, if we've got millimeters of mercury, 6,800 HGs, and we want to convert it into ATMs, well, 1 ATM is equivalent to 760 HGs. And so we end up with a pretty high pressure, 8 point, we got what, 266, okay, 8.9 ATMs. Great, so let's look at some other fun laws that we have. So the next law is called Charles' law. And this law is going to relate volume and temperature. This explains why hot air rises. If we have like a hot air balloon, for instance, what's happening is a real life example of Charles' law. So the gas inside is getting heated up by this flame. And when you heat the gas up, the volume increases, right? It takes up more space. And if you have the same amount of gas taking up more space, you're actually lowering the density. Well, lower density things will float in higher density or atmosphere around it. So when looking at Charles' law, we're not going to talk about pressure and we're not going to talk about amount of gas. We're going to say that those things stay relatively consistent. We're going to look at volume and temperature. Now it's important that your temperature be in Kelvin. Okay, so we have some play with volume and pressure. We can, change those, use mmHgs or use milliliters, but temperature has to be in Kelvin. These equations will not work, Kelvin. And remember Kelvin, if we have Celsius, sorry, let me rephrase that. Kelvin is equal to our degrees Celsius plus 273. This is why we can't use Celsius, because to go from Celsius to Kelvin, it's not a multiply and divide, it's an addition subtraction, which is a different level of order of operation, so it won't work. All right, if we look at a gas, and if I go ahead and I cool this gas down, what I'll find is as the gas gets cooled, the gas gets smaller, or the volume it takes up gets smaller and smaller. At some point, what we expect is that if the gas hit absolute zero, which is Kelvin at 0 degrees, that the volume of the gas would be zero. That's why we can't get colder than absolute zero or 0 degrees Kelvin, because if we were to go below that, what would happen to the volume of our gas? It would actually take up a negative volume. We're not going to take up a negative volume. So absolute zero is going to be the coldest temperature that we find. Charles' law lets us know that volume is directly proportional to temperature. So volume, if volume increases, temperature is increasing. If temperature decreases, the volume will decrease. Like we've got this balloon here, okay? So let's take a balloon and put it in an ice bath. If I had a balloon and I put it in an ice bath, it's getting colder. The balloon would sort of appear to deflate. It's not actually deflating. It's just that the gas particles are moving closer together because they don't have as much kinetic energy, right? So they're not like flailing all over the place. They're kind of a little bit more subdued. If I was to take the same balloon and put it in boiling water, the opposite is happening. We're heating this up. We're pumping kinetic energy into those particles. They're going crazy. They need to get away from each other. So they're going to take up a larger volume. So here is the equation for Charles' law. V1 over T1 equals V2 over T2. So a little different than Boyle's law where they were sitting next to each other. Here we've got a fraction bar. And that tends to give some people trouble when they're isolating for T2. So I'm gonna, or T1. So I'm gonna have you do that, all right? I want you to get, let's do T2. I want you to get T2 by itself. So here's T2, get it solo. Actually, I'm gonna move this over to my whiteboard. So it's easier for me to write. Nope. All right, so Charles' law, we've got constant pressure and amount. Temperature is directly related to volume, and the equation V1 over T1 equals V2 over T2. What I want you to do though is get that T2 by itself. I'll give you 4 minutes for that, 4 minutes. Okay, so the thing that's tricky about isolating for T, it's not really tricky, but the thing that you have to know is that the T2 is below this fraction bar. So what I see happen a lot is people will say, oh, V2, okay, I'm gonna divide this by V2 and I'm gonna divide this side by V2. Those go away. And then what they'll equate this to is they'll say, well, V1 over V2 times T1 is equal to T2 and I'm done. But it's not, because look, T2 is below the fraction bar. So this is really 1 over T2. So if I want to get T2 back up on the top of the fraction bar, I have to do the inverse. I have to flip-flop these and I have to flip-flop these. So T2 is actually equal to V2 times T1 over V1. Does it make a difference? It totally makes a difference when you're plugging things in. So make sure you are being mindful of your isolation. Being mindful of your isolation. Where did that come from? Just make sure you're isolating your variables correctly. All right, here's a problem I want you to do. A sample of gas has a volume of 2.8 liters at an unknown temperature. When the sample is submerged in ice water, and so we're going to assume that the temperature is 0 degrees Celsius, its volume decreases to 2.57 liters. What was its initial temperature in Kelvins and Celsius? And we'll assume a constant pressure, right? And if it's a balloon, it's a sealed balloon, it also has a constant amount. So I'll give you guys, give you 5 minutes for that. All right, so for this one, you have an initial volume You don't know the initial temperature. That's what you're trying to find. And you do have the final volume and the final temperature. Make sure your temperature is in kelvins. So go through all this. Okay, so we've got our equation. We're trying to find the initial temperature, this T1 down here. So for isolating that variable, you should have gotten that T1 equals your initial volume divided by your final volume times your final temperature. Your final temperature is at 0 degrees, right? It's in an ice bath. We add the 273 Kelvin. The volumes just need to be in the same units, and they happen to be in liters and liters. So those will cancel, and we'll be left with Kelvin. So we get 297 Kelvin. The problem says, oh, if it says I want it in degrees Celsius, even if it gives it to you in Celsius and it wants it in Celsius, don't put Celsius anywhere near this equation. So we will have to reconvert it into Kelvin, or rather Celsius, by subtracting 273 after we get away from the equation. First you get your Kelvin, then you do your Celsius. There's a combined gas law. So this sort of smooshes Boyle's law and Charles' law together. And it's going to be P1 V1 over T1 equals P2 V2 over T2. This one is fun because it has 6 variables. So you will be given 5 of the 6. What do you notice is missing from here? Any sort of N value, N being an amount of the gas. So we're assuming that the gas has the same mole value. Let's say we had 1 mole here and 1 mole here. But the pressure is changing, the volume is changing, the temperature is changing. So let's have you work on this one here. So a sample of gas has an initial volume of 158 milliliters at a pressure of 735 mmHgs and a temperature of 34 degrees Celsius. If the gas is compressed to a volume of 108 milliliters and heated to a temperature of 85, so we can see that our volume is decreasing and our temperature is increasing, what is the final pressure in mmHgs? So I'm going to have you work on that. Let me step back real quick. So if you didn't write this equation down, write it down. P1 V1 over T1 equals P2 V2 over T2. And then go ahead and apply it to these values here. Give you 4 minutes or so for that. Okay, so in this one, we're going to be using the equation that is the combined gas law. You know your initial pressure, you know your initial temperature, you know your initial volume, and then we know final temperature and final volume. The final pressure is what we're trying to solve for, so we need to isolate that P2, move the V2 to the bottom, move the T2 to the top. So the new equation should look like this. P2 is equal to P1 times V1 times T2 over T1 times V2. Sometimes it gets tricky with all those ones and twos. Make sure you're keeping those as connected to the right variable. Change your temperatures. So T1 is now 307 Kelvin, T2 is now 358 Kelvin, and then plug it in and make sure you add all of your units. And you'll know if you did it correctly, right? So Kelvin and Kelvin cancel, milliliters and milliliters cancel, and you're just left with units of mmHg, which is a perfect value for pressure. So we get 1.25 times 10 to the third mmHgs. Last law that I want to talk about today is Avogadro's law. So this relates volume and amount of gas or moles. So we're going to assume with Avogadro's law that temperature is constant and pressure is constant. I'm not changing those two things. This is sort of a no-brainer. There's a direct relationship. As you increase the amount of gas or the number of moles, you increase the volume. Think about when you blow into a balloon. What happens to the size of the balloon or the volume of the balloon? It gets bigger because you're putting more gas into it. So it doesn't give us the equation, does it? All right, so the equation for Avogadro's law is, so Avo's law, we're going to assume constant temperature and constant pressure. Kind of ignore those guys. And we are going to find that our volume is directly related to the amount of gas. So V1 over N1 equals V2 over N2. Volume on the top, and then N is amount, and make sure you note that amount needs to be in moles. So we've got a problem here. Let's say we have a 4.8 liter sample of helium gas, which contains 0.22 moles of helium. How many additional moles of helium gas should be added to the sample to obtain a volume of 6.4 liters? Assume a constant temperature and pressure. So in this one, we know our initial volume is 4.8 liters. We know our initial moles as being 0.22 moles. How many additional moles? So we're not talking about the final moles. We're talking about how much we had to add to get to that final value. So that's an important thing we'll look at the end here. But our final volume is going to be 6.4 liters. So let's figure out what the ending value of our N2 is. So our ending value of N2, when we plug it in, N2 is going to equal your V2 over your V1 times your N1. The liters will cancel, and we get 0.29 moles. Now, the problem specifically said how much or how many moles did you need to add to get to this value. So we started at the 0.22 moles. We ended at the 0.29 moles. So we're going to subtract those two from each other to get that final value of 0.07 moles. Or we added 0.07 moles to the 0.22 moles to get to the 0.29 moles. So when you're working with Avogadro's law, that may be a thing where it says, hey, in actuality, I don't want to know the final value. That's not enough. I want to know how much you had to add, just an additional subtraction. Okay, so we're going to stop there. I'll get into the ideal gas law where we kind of smush all these things together next time. If you have any questions, stay around. Otherwise, enjoy the rest of your day. Do know that the last day to drop the class is, I believe, Wednesday. So hopefully no one is dropping. But if you feel like you need to, this semester has been a real struggle, know that that is available for you. Otherwise, enjoy your day.